A big hello to all you savvies out there. In today's episode of Electronic Savvy, we take a look at the layout design of a portable 12-volt boost or step-up DC-DC converter with variable source voltage. We will look at the board stack-up, component placement, ground stitching, and many more of the best practices for EMI optimization and power integrity. But before we get any further into the design, I'd like to thank our today's sponsor, PCBWay. If you're looking to turn your electronics projects into reality, PCBWay is the place to be. They offer top-notch manufacturing services, fast turnaround times, and excellent customer support. So whether you're a hobbyist or a professional, PCBWay has got you covered. Check them out today and turn your ideas into reality. Welcome back, you guys. Today we're gonna go through the layout design portion of this portable 12-volt boost converter. I'd like to divide today's video in three main sections. We first gonna talk about the board stack-up, things like layer count, layer thickness, layer names, and similar fun stuff. Then we're gonna tackle the component placement, things like placing input bulk capacitors, the main switcher IC, decoupling caps, and the main magnetics, or the inductor and input caps. And lastly, we talk about routing and via stitching. First things first, let's take a look at the stack-up for this 5-volt boost converter. As for almost any typical basic switching regulator design, we define 4 symmetric copper layers as the main building blocks of the board, followed by 2 pre-peg layers, a core layer, all sandwiched by ENIG, which is an electroless nickel immersion gold metallic foil, as well as solder mask and silk screen layers. So this is what the board stack-up look like. The total thickness of a standard board adds up to around 1.6 millimeter or 0.63 inches or 63 mil. Now looking at the main copper layers, we call the top layer or layer 1 top, and that's where all the main components such as the ICs and the passive sit. The next copper layer is the inner layer 1 or ENT1, separated by top layer by a pre-peg or dielectric layer, which serves mainly as the reference or return current plane for the adjacent layer, particularly the top layer in this example. And for the best power integrity and better EMI, minimize the distance between layer 1 and 2, which in turn will shorten the formed current loop, consequently smaller stray inductance, and increase the built-up capacitance, consequently more effective noise filtering across the top 2 layers. The third layer, or the second inner layer, ENT2, serves as auxiliary signal or power plane, where I use mainly to route power planes or additional signal traces across the board. And finally, layer 4 or bottom layer is the only other layer than top layer which physical components can be placed on. For this board, I allocated bottom layer for placing the coin battery surrounded by large ground polygon to help with simple ground stitching later in the design. So this wraps up the stack-up. Going back to the layout view, when it comes to the component placement, assume your PCB is a black box and you need to visualize where the power or signal comes into the box and what goes out. One of the most crucial aspects of layout design is understanding your inputs and outputs, as it determines the location of most components on the board. Looking at our board in this video, we have a main USB connector as our input and all its associated components such as the diode ore and decoupling caps and terminating resistors. Then the boost switcher IC and all its passives around it. And lastly, a 2-pin terminal block as our output. So now we have a rough understanding of where the main blocks within this box reside. The next step is to evaluate where to place the passives around these main blocks or the ICs. First is the USB connector. Theoretically speaking, any active connector requires some kind of ESD, electrostatic discharge, or TVS, transient voltage suppression diode, as well as a bulk capacitor due to the potential presence of human touch and long connector cables. ESD or TVS diodes is a fast reacting diode which gets biased at the presence of high voltage spares due to electric discharge, somewhere in the range of thousands of volts and clamps the high amplitude spare to a level that the components downstream can tolerate. Bulk caps, however, act as a local charge reservoir that controls sudden changes in the current while balancing the voltage on the power bus to avoid voltage drooping. Voltage drooping is the incident where the voltage drops below its desired value because of excessive current demand. In this design, I decided to use a fast 10 picofarad capacitor to act as a TVS diode. Capacitors with small value appear short or with low impedance to high frequency, high amplitude noise and are indifferent to nominal DC voltage. I then paired that 10 picofarad cap with a 10 microfarad bulk cap to take care of radiated emission noise along the USB cable. It's important to place the lower value cap closer to the USB power pin so that high voltage spares get shunted through the cap to ground before traveling downstream and potentially damaging a component. We then place the bulk cap right next to the 10 picofarad cap, though not as crucial since we're not sending any data over USB in this board, for example. I went ahead and placed termination resistors R7 and R9 right next to the USB data lines as the right practice. We then placed the ideal diode IC, U2, preferably close to the connector, and then placed the decoupling caps C13 and C14 right next to pins 8 and 6 of U2 respectively for the most effective noise filtering and decoupling. Now we're going to talk about the most important placement guideline of the board, which is the boost converter stage itself. As mentioned in part 1 of this video series, input and output caps both play an important role in noise and ripple performance, as well as stability of switching regulators. However, in this case of a boost regulator, since the magnetic or LC filter stage of the converter is on the input side, then selection and placement of the output caps are more crucial to the proper operation of the converter within the specs. So in this case, if we had to pick between more stringent requirements on placement of input versus output caps, the output caps take the priority. So with that said, let's take a look at the design. The input stage consists of input caps C15, C1 and C2 as well as L1. Inductor L1, ideally shielded by package, must be placed close to the switch node of U1 or pin 1 to minimize the high DI over DT switching current loop, which can cause EMC or electromagnetic compatibility failure. Furthermore, the output stage consists of output caps C6 through C10. Note the capacitance values. Assuming the same package size, larger caps have smaller ESR, which is the equivalent series resistance, and lower resonant frequency, while smaller caps have larger ESR and higher resonant frequency. Therefore, it's recommended to bundle up different values of high-quality ceramic caps for good noise, ripple, and stability performance over a wider frequency band. 100 picofarad caps, for instance, take care of most of the high frequency noise on power line versus 22 microfarad caps, such as C9 and C10, take care of lower frequency noise and help with better transient response. Now that we finalized the placement of input and output stages of the switcher, as well as the diode O-ring circuit, we can then place the decoupling caps, bootstrap cap, RC components of the compensation network, and feedback divider circuit. I, for instance, have placed decoupling caps C3 for the VCC or internal supply rail of the IC, and the bootstrap cap C4 for providing high enough voltage for proper operation of the internal N-channel high side FET, right next to the chip with the shortest trace to minimize noise coupling. So this wraps up the placement of all the major components on the board. In addition, there are a couple other miscellaneous components as we've seen in the schematic section of this video, such as the LED indicators, resistors, and a push button, which can all be placed on the board with looser restrictions as they are not in the way of main power or signal flow, hence don't directly impact power or signal integrity. So far in the video, we've covered the board stackup as well as the component placement, and now we're going to talk about routing and physically connecting the components as part of the layout design. For the best power integrity, or PI, place the smaller cap, lower value and smaller package size closer to the pad of interest and place ground vias right on the pad as shown here to minimize the loop area for return current to travel through. As you can see, I've followed these two simple rules in the entire design regardless of the IC type for the best practice. Capacitors placed next to sensitive IC pins are also called decoupling capacitors, as they decouple noise or high frequency components of the power or signal away from the pin of interest. I recommend using copper pores, aka solid regions in Altium, to connect higher current nets on the board, as it also provides flexibility in defining custom shapes for copper planes. I connect VN nets as well as USB power, Vout, and the inductor switch node, all via the solid region tool in Altium. Every other passive net can be connected via 7mm minimum wide trays for easier manufacturability. Once done with the placement and routing, the last step is to fill the empty spaces all around the components on top and the adjacent layers with ground. The quickest way to do this is go to the navigate bar, then to place, then polygon pour, or PG for short. And once this plus sign shows up on your cursor, you are ready to define the border for this polygon. So you can just go ahead and left click, just define it however you like. Every time you press the left button, it sets a corner of this pour. And then once it's done, you could hit right click and it will automatically connect the ends together. And here we go. Here we have a polygon pour now. And once that's done, you go to the net bar under properties and type the net that you are interested in. In this case, it's the ground net. Hence, I put ground. This way, Altium associates this particular ground pour, which you created using Polygon Tool, to the ground net. This is also a smart tool which will pour around the nets different than ground, so you don't have to worry about it causing short or fabrication flaws. That said, you should still check and make sure that the design was done properly. This assumes the design rules are set properly though. I can make another video on Altium Designer's design rule if you guys are interested, and we can talk about all the constraints and design rules within Altium and how to set them. Once we have poured ground all over the board in every layer, as we have done it here, you can see on layer 1 we have ground all over, layer 2 we have solid ground, layer 3 we have ground, and layer 4 we also have ground all over the board. So once that's done, the one last touch is to stitch the ground pours in every layer together. That can be done by navigating again to tools, via stitching or shielding, and select add stitching to net. Once you select that, we can set the clearance rules, how far we want the vias to be placed apart, and we can set the net names right over here, the style of the via, and the particular size for via hole and via size. Once everything looked good, once all finished and done, go ahead and hit OK, and Altium will automatically sprinkle as many vias as defined in the constraints on the board, connecting the ground pours all together. This action will ensure the board ground to have the lowest impedance across the board, which then significantly improves PI and SI. So this wraps up a complete overview of the layout design portion of this portable dual supply boost converter. We've talked about board stack up, component placement, as well as layout design, best practices for improved power and signal integrity. If y'all enjoyed this type of video, don't forget to drop a like, leave a comment, and subscribe if for some reason you have not yet. And thanks again all for watching. We'll catch you all in the next video. Peace out.